It's my pleasure to introduce him. We have started collaborating recently, and I'm eager to learn more of what he's doing, not just reading about it, but listening firsthand. So Ivano is Associate Professor in the Department of Computer Science and Director of the Network Institute at the Vrije Universiteit Amsterdam. His research interests include data-driven software engineering with a special emphasis on software architecture, mobile software development, and robotic software. And that's why we are here today with him. And he received his PhD in computer science from University of L'Aquila, Italy, and he's member of IEEE, the Association of Computing Machinery, Versem, Amsterdam Young Academy, and Amsterdam Data Science. Without further ado, floor is yours, Ivano.
Okay. Can you hear me? Okay, cool. Okay. Hi, everybody. The title of my talk is How to Architect Robotic Software. I'm not going to teach you how to do your job, so don't be frightened by the title. I'm going to tell you the information that we extracted from some open source repositories targeting mainly ROS. Okay, so I don't have the the wish to teach you your things. This is more or less already a disclaimer before I start talking. This is my background. I worked primarily on software architecture since my PhD back in those years. And I think this quote nicely summarizes how I see software and why I think software architecture is important. Because as we discussed already this morning in a pretty extensive manner, the decisions that you take at the architectural level might have very long and impactful consequences on the whole lifetime of your system. Okay, whatever system it is. I'm working on robotics since some years. I think I have a slide for, about that later on. But I apply more or less the same principles and the same way of working, methodologies, to other types of systems, from microservice-based systems to Android applications and others. Robotics is one of the, my playgrounds where I try to do my architectural things. I started to work on robotics. If I remember well, it was in 2013, where we worked on a product that was called Flyaku. Actually, it's still existing, but it remained like a research prototype. And the idea was that you, as a user, you could see a web interface similar to this one with a map, where you could draw the areas of interest together with some other important areas for your mission, which is, for example, a no-fly area or an area in which you want to be very precise in taking some measures. And here on the right part of the UI, you could specify, okay, today I'm going to use 3 drones, I'm going to use 2 drones of this type, other 2 drones of this other type, and then pushing a button, we were able to generate detailed flight plans for each single robot, so splitting the areas according to the robots that are available, and to execute the mission. So taking the telemetry from the robots and checking if what we generated in terms of trajectories of the drones was actually correct and working properly. Okay, this is now something like we give for granted. So if you are familiar a bit with products like ArduPilot or some other a bit more advanced control stations for drones, this is something like the default. Almost 10 years ago, this was research material. Okay, so this is where I'm coming from in the from robotics. And here we were already playing around with ROS, which is you know what it is. So I'll go ahead. Fast forward to today. I'm part of the Software and Sustainability Research Group in Amsterdam. which is called S2 for friends in short. And our idea is to try to make software energy efficient and as sustainable as possible. We have different, let's say, specialties. In my case, it's on focusing on the energy efficiency of software, measuring it, and try to come up with guidelines and, let's say, indications for developers in order to make their software more energy efficient. Yes. Since I know it's after lunch and you might be bored, I give you firstly something that might be useful in addition to all the concepts that I will tell during the discussion, and it's a tool. So the tool is called Robot Runner, and the goal is to allow you to configure an experiment targeting a specific type of robot, and then the tool will take care of the automatic execution of the experiment. So I hope that this tool might be useful for you. You know, at some point you will need to evaluate your algorithms, your systems, or your whatever. So this, the goal of this tool is really to help you in saving some time in executing the experimental part. So how does it work? This is, let's say, a very high-level overview of the tool. We take as input some configuration of the experiment. I will show you what is a configuration of the experiment. Then there is an experiment orchestrator component, which reads the configuration, and it executes the robotic system together with some profilers that are in charge of collecting measures during the execution of the mission. This part, which is a bit more grayish, I don't know if you can see the difference between the colors of this and these other ones. Can you see? Okay. These are plugins. So this means that if at the moment in which you need a tool, there is no plugin for example, measuring the energy of a robotic arm, for example, you can develop a plugin so that other people can use it, and you can still reuse the generic business logic of the tool for orchestrating the experiment. The output of the tool is a run table. I will show you an example later, but basically it's the set of the measures that you collected during the experiment. So let me show an example of the configuration. The configuration is based on Python. So the idea is that you develop a class in Python, which is extending, here is not specified, but it's extending a base class, where you implement, override actually, specific methods that we provide in such a way that then you know what to do in specific points in time during the experiment. These points in time are the ones that you see here. So this is a visualization about how we see how an experiment in robotics is performed. So we have a moment that is before the execution of the experiment. So here you usually put, the configuration that will remain the same across the whole duration of the experiment. For example, if you want to bring up a proxy, or if you want to throttle the network in some way, or if you want to do other things, you want to launch, all the ROS platform, the ROS system. And then the experiment is seen as a sequence of runs of the experiment. And then we have again here some other points that might be interesting for you, which is before the execution of a run, when you want to start the measurement, when you launch the mission, and then the corresponding closing parts. And we have the after experiment. So the idea is that for each of these events, we provide an abstract method that then you can implement by adding your own business logic for the experiment. Once you implemented these methods and you configure the experiment, you launch the Python script, and then it will be everything managed by the tool. Yes. So here I will go pretty fast. So if you have any questions, just raise your hand and we can discuss it. This is an example of how you can populate one of these methods. So this is for the event populate run data, which is this one. So this is the moment where we basically finished to have one run of the mission, and we are collecting some values from some files that you can see here that are created by one of these guys here, the profilers. We do something. That something is up to you, of course, because the experiment is yours. We don't know all the specifics of your experiment. We just provide, the orchestration logic. And then you populate in some way with this, let's say, API, the run table. And this is one example of the run table. Here we have, for example, 14 runs of the experiment. We see that the status is done for all the runs. In the first run, we have a task that is called networking. So don't look at the specifics, the specific meaning of these elements, just get the idea. The second one is computation, video, networking. So you can see this as some kind of, the treatments of the factors of your experiment. This is repetition, sorry for the typo here. So this means that if you have some basics in experimentation, I'm pretty sure you have it. You cannot just do, okay, I run my system with this specific configuration, I take the result, and then this is my data point that I'm going to analyze. You need to do some repetitions in order to, increase the statistical power, and in order to be sure that your data is not subject to some influence that is coming, for example, from the environment or from the operating system or whatever. So usually we repeat many times the same configuration to be sure that the data is trustworthy. And here in these columns, you can see the values that have been collected in the specific run. So here, for example, we have the mean of the CPU usage. Here we have the mean of the memory usage. And here we have a computation of the energy consumed by the robot. Yes?
Just one question, Ivano. Would it make sense I don't know if the robot runner already does it, but would it make sense to give this CPU memory energy measurements and then tell you how many measurements to do to reach some statistical validity, for example, based on certain statistical strength that you're interested in? That could be a plugin, right? And sorry to interrupt, but I'm in the same group, so I should know.
It can be a plugins in this specific tool are only for taking the measures, because these are the things that are probably the ones that you want to reuse in other experiments. So if I develop a plugin for the INA 219 for energy, it's a small board and a sensor for taking energy of the robot. It's probable that some other people in some other groups need it as well. The specifics of what you ask, I think, are specific to the experiment. So these go somewhere here. So you need to implement it yourself.
Can I disagree?
Yes.
No, I think that maybe I was not clear. The number of measurements that you have to do to reach some statistical validity, right? This is something that is now input to the specification of an experiment.
Yes.
I was thinking, what if you don't provide this as an input, this number, but you give some exemplary values of some previous runs, so you can calculate some variables.
This can be an easy preliminary step that you can do.
I
Yeah.
think it's not specific to the scenario that you run. It's more like something that you can really use.
Currently, at least in empirical software engineering, we do this kind of, this is part of the design of the study. Yeah. And you don't want to take a decision based on the data. You want to take a decision that is not influenced by the data that you are collecting. So you do the full design firstly. You try to put everything, black and white, so that even subconsciously you are not influenced. And then you move to the execution of the experiment. Usually we don't go the other way around. But technically it's possible, yeah. Other questions? Okay, I move on. So this is an example of an experiment that we did. It's not yet published, so don't take pictures. Just kidding, but it's not yet published. This is I think I can play the video. Let's see if it works. Yes. Okay, it's a very basic system, different from the super macho system from TNO. Here we are exploring an hypothetical museum, and the robot is moving around and looking for specific paintings in the museum. And what we wanted to understand in this experiment is, okay, let's try to move some of the ROS nodes, specifically either the G-mapping one for one of the SLAM implementations, the move base, or the one for doing object recognition. And we are thinking, okay, what happens if we are moving some of these nodes to the cloud? That is, not running them on board the robot, but to run them somewhere else. What is the, the trade-off between, how much networking I'm doing, how much CPU I'm using locally, and if there is some gaining. So just very quickly, these are the results. We have a 60 pages paper on this, so don't ask me clarifications. I can send you the preprint of the paper, signed in blood that you're not going to share it. But the interesting thing that we notice is that for navigation, for offloading the navigation task, so basically moving the move base node to the cloud, was not impacting too much the energy consumption of the robot. But when we were doing the same thing with the object recognition node, we noticed that the robot was consuming less energy when the algorithm was running locally in the robot. So in a way, basically, actually was running in the cloud. Sorry, so offloading is true. So in a way, in this case, networking is, from the perspective of energy consumption, is dominating the CPU usage. So, and this is the kind of experiment that we try to do. So if you were wondering where to put these nodes locally or in the cloud, so with our experiments, we try to give answers to these doubts. Okay? Okay, now let's move to the architecting topic. So this was meant as a warm-up, to start talking about which might be the kind of problems that we are looking, how we approach problems. So we try to be as empirical as possible, meaning that we don't want to give opinion to help you in taking the decisions from the architectural perspective, but we want to put the science in your decisions, okay? So you don't say, okay, I feel like I should put the move-based node in the cloud because it's more convenient. You should take, or us should take decisions based on the actual numbers and what we expect. Okay, so this part of the study is based, of the presentation is based on 3 studies in collaboration with Carnegie Mellon University. The first 2 are basically the same study, where the first one is being published at a conference, and the second one is we go a bit more into the details in a journal publication. And then the other one is slightly different. We look at architectural tactics and to an experiment on those tactics. I think you are expert in ROS. You are knowledgeable at least in ROS, so I will not spend any time in telling you what ROS is. Can I? Do you panic? No, it's fine. Guys, I'm sure you know.
They had as homework some tutorials, so
okay.
At least they should know the nouns,
okay.
The concept.
Okay, so we go straight. So the motivation is basically this. This is a visualization of a basic robot that I'm pretty sure you know. This is the computation graph of this robot. In these specific studies, what we mean by software architecture is something similar to this. So we want to see how nodes, topics, and services, and all the other primitives that you think in ROS, how they are organized in real software systems. And then by looking at many of those systems, we try to come up with some guidelines to help you in better structuring these kind of systems. The problem that we want to solve is that this is a very basic robot, so it doesn't have a lot of intelligence, or it's not super complex. But already from the, if you look at the architecture, at how these nodes are organized, it's not super trivial. If you want to be sure that a crash here is not impacting something else here, the problem starts to be a bit complex. Okay, so in short, the problem is that, as you know already, the computation graph of ROS-based systems is getting bigger and bigger, and with more connections, making it very complex to understand what is actually really going on at runtime. And I also see sometimes when I go online, I see things like this. So people doing printfs to see if the system is working. So here we see, a problem, because on one side we are building monsters that are getting bigger and bigger. On the other side, we are still a bit more in the arts and craft phase for developing this kind of software. I'm in software engineering, so if you ask me what is a control algorithm or something, probably I don't know. But I see problems from the software engineering perspective. So really how to take decisions on the structure of your code, how to make it maintainable, how to make it, controllable from the performance perspective, energy, that is especially important for us. So we try to push a bit more the practice of developing this kind of software. So what did we do? We want to look at how people are working on real systems, and we are going to look at GitHub repositories. Then we extract what we call design stimuli and the applied solutions. And then at some point, we build a catalog of guidelines that are basically generalizing the applied solutions. So this is the intuition of the study. Here is some examples of design stimuli. So for example, this one, upgrading the navigation package will not impact the whole system. So in a way, I don't want the navigation package to be, to have all the dependencies across the whole system, because if tomorrow we will have the nav14 ROS package, then I don't want to change also other things that don't have anything to do with navigation. Okay? So this is just the intuition. I'm making it super trivial. How can I efficiently check that all nodes are always up and running? There are ways in which we can do it. There are ways in which we can organize the system in such a way that this is easy to do. Okay? And there are architectural tactics for this, which we will see later. Or we can ask questions like this. Sensor data is slow. How can I improve it? Are there some ways in which still fixing the functional sides of my system, so it still does exactly the same things, but internally it is organized in such a way that I'm improving its performance. And improving the performance here, I'm talking about the doing it from an architectural perspective. So I'm not talking about improving the specific algorithm for data fusion, for example, but I'm talking about, okay, let's add an intermediate node that does the data fusion on a dedicated node, for example. Okay? So it's more on the, let's say, bird view perspective of the system. Okay, this is the methodology that we followed. So we start from a set of repositories. We constructed the dataset by mining them from basically GitHub, Bitbucket, and GitLab. We extracted some data, we analyzed it, and this brought us to some preliminary results. Let me see if I have, yes. For each repository, we analyzed all markdown files, all external links, and all stored documents. Yes, this was a bloody work, but I hope it paid off. I will show you some results later. Then we closed the loop. We went to the developers of these repositories where there was some architectural activity, and we asked them to fill a questionnaire to understand the why, we were seeing something relevant here. Okay? And here, methodologically, if you are into the methodological parts of studies, we did collaborative open coding and thematic analysis. I won't bore you with this. The main research questions that we wanted to answer are the state of the practice. So by looking at this, we could say, okay, in open source projects targeting ROS, the situation is like this. Okay, and I will show you a couple of slides about that. And then the core of the study is the guidelines. So as I said before, the goal is to build this catalog of commonly applied solutions in such a way that, you know, the smart ideas, instead of being, you know, hidden in some obscure repository on GitHub, they are, you know, elevated and made available to everybody. So that's the mission of the study. I will go very quick on how we started from the three platforms that you see here, and how we did all the technical steps for filtering them in order to be sure that we are looking at actual ROS systems that are not, for example, tutorials, demos, or whatever. So I will go very quick on this. What you need to remember is that we were very rigorous and systematic in all the steps, and we collected all the data, and we are making it available in the replication package of the study for everybody to inspect it. And I think this is, you know, the basics of science, where the results that you show are not, you know, only the end result. You need to show the whole trail of the activities that you did for achieving those results. And the second thing that you need to remember is that we came up with 335 repositories containing real ROS-based systems. This is it. So let's give a look at some of the projects. There are some obvious ones, like Turtlebot 3, some repositories coming from ClearPath. There were also some other interesting projects that I didn't know, but probably you do. Duckytown, that is, you know, a kind of education system based on ROS. And we had also some commonly used packages, stacks, for some parts of a robotic system. The goal here is not only to look at the you know, systems in a very, let's say, specific manner, so looking at only at the robot, but also looking at what have been called this morning subsystems. So, like for example, cartographer usually is used as a part of a bigger system, no? So this for us was also a system, okay? Because the decisions that have been done here in this, from an architectural perspective, can still be useful for someone in their own system. Guys, probably you know this. We discussed about this on this course. Okay. This is an overview of the types of systems that we look at. We have some ground robot. Some are generic packages that could be applied to any type of robot. Others are manipulation, so robotic arms primarily, aerial robots, service robots, and so on. In terms of capabilities, we have, this is what we had. We have some repositories that were specifically for the control part of the robot, others for planning, vision, navigation, you know, basically what we might expect. So really not big surprises here. But it's good that we don't have any, you know, big spike or some imbalance here, because we want also to be, you know, representative of as representative as possible of the robotics development domain.
Could you give an example of what, I guess it's development support, that category 14 systems?
Yes, like loggers.
The ROS system with launch files, that's non-trivial for development support. That really piques my curiosity.
Sorry, I got.
You mentioned the requirements, right? A ROS system with launch files.
Yes.
Which is non-trivial, and then it's for development support. So that makes me curious. What is that?
If I remember well, okay, here the category is about subsystems that are, let's say, supporting, that are not providing any first-class functionality to the robot. So you can have a part of the system which is, for example, some ROS nodes for monitoring the other nodes of the system, logging, or, you know, I don't have, doesn't come to me.
Execution tracing, I guess, also.
Sorry?
Execution tracing, that sort of thing.
Things like this,
Right,
yeah.
okay.
So not providing functionalities, but supporting the development.
Right, yeah,
Okay. Yes?
How did you distinguish the packages or repositories based on planning navigation? Did you analyze the message types, or?
We looked at all Markdown files in the repository,
Okay.
all the documentation linked from the repository, and all the documents, PDFs mainly,
So it was
stored
done
in the repository.
manually, basically.
Yes. And we did this, we were 2 people doing this, plus 1 checking how we were tagging the repositories. Still for the sake of, you know, robustness of the study and the replicability. Other points? Okay. Okay. We also looked at how people are documenting the architecture of a ROS-based system. So what we noticed is that over the 335 repositories, 220 were not documenting the architecture at all, not even the list of nodes and topics. So plain greenfield. So I think there is some work to do for us in this area. Some of them, and then for the others, we had some partial representation of the architecture. Here I'm meaning that at least we know what are the nodes and what are the topics, services, the provided services, or, you know, talking in ROS language. But we didn't know who is talking to who. So there was, you know, just the list of topics, for example, exposed by the system. The rest is more blurry. When we say yes, we have a clear picture of what is more or less the computation graph of the system. And here I'm showing some examples of the architectures that actually the descriptions of the architectures that we extracted from these systems. And here you can see all kinds of types, ranging from the plain old computation graph to some more box and line representation, something in between with some external, you know, the hardware specified contextually also to the computation graph, and some other visualizations. This is already interesting because we can see that people when they talk about architecture documentation, they might think about different things, okay? From the computation graph to a layered architecture, or, you know, other kinds of representations. In the replication package of the study, you can see all architectures that we extracted, and I think this is already something that might be valuable for you, as you know, if you feel like you need to represent the architecture of your system and you don't know how to do it, you might take some inspiration from these examples. Okay, this is mostly about which type of elements were documented in the architecture. We have nodes and topics, obviously, as the most recurrent elements. We have the parameter server that is represented quite often. And then we have all kinds of other things intermingled with these more recurrent ROS-based concepts. And here, while we were looking at the documentation, we were also looking at how, let's say, quality attributes or non-functional requirements, as described this morning, are at least mentioned by the contributors of these repositories. And here we have maintainability as a winner. And then we are followed by reliability and performance. So this is basically kind of related, you know, to the domain. So you want your robot to don't crash if it's a flying robot, for example. And then we have other types of quality attributes that have been at least mentioned in the repositories. We have also one on energy, but we are working on it to make robotics a bit more aware that we can work on energy as well. We also collected from the questionnaire why people are not documenting the architecture of a software of the robotic system. Here, I'm not going for the sake of time through all the details about all the types of categories that we saw, but I think here, from the perspective of a researcher, this is a very important point of the study, because here it's clear that there is something missing. Okay, we can have, for example, people that recognize that it could be nice to have an architecture, but we have no time, so we need to move on with the implementation. Doing the architecture is perceived more as a kind of overhead with respect to standard development process. The system might be too small for describing the architecture, fair enough. The source code is informative enough. I don't fully buy it, because there is evidence that when you see a properly documented architecture, then your reasoning, the design decisions that you take are way better than looking at working directly on the code. Okay? So this is something that we need to work more on the awareness of people about the importance of the description of the software architecture.
Unfortunately, the source code is enough. Is more people that is defending agile methods defend that the source code is enough.
Yes, it's a thing. But there are also opportunities. Like if someone is saying, okay, we don't have the resources, we might have some space for having some approaches for automatically documenting the architecture. I'm talking as a researcher, I try to help developers in doing something that they cannot do because of time, for example. So we might think about having some ways in which we can have an automatic description of the architecture. This is also supported by the fact that architecture is unstable. So in a way, what these people are saying, that if I spend like 2 days in doing the architecture documentation, and after 1 week the documentation is old, then it didn't pay off. No, it doesn't make any sense. But if you have something that it's automated, or at best like integrated with the continuous integration pipeline, and they have a good enough architecture description for free, probably in that case it might help in at least raising a bit the level of abstraction in which decisions are taken. Okay, this is just free thinking. So I'm reporting the data, and when I speak my opinion. Yeah, and there are some other interesting points, like no clear advantage, the architecture is not clear, the system has a standard architecture, so don't know exactly, but okay. Here, yeah, I added a couple of pointers to some already existing approaches for extracting the architecture of ROS-based system. ROS is a static one. You still need to build the system, so that is still requires a bit of work. But with this, you can take the source code and the launch files of the system. You can get some nice visualization. And of course, dynamic one is you can just launch the system, and then you get the computation graph using RQT graph. That would be, the first steps if you want to think about how to automatically extract the architecture.
I have a question about the RQT graph for you, Ivano, but also for the ROS professional developers here. Also related to a previous graph that you saw, in which the architectural elements that were most commonly documented were nodes and topics, but then services were way lower in the list, and the RQT graph doesn't capture the services. And I'm curious, from the practitioner's perspective, how often do you use services? Is that they are just not that used by the ROS community? They are not. 80s. So, and they are not capturing the architect in these tools for the architecture, so you are missing half the system, basically.
Also ROSBEG files, if I remember well.
Sorry?
In ROSBEG files, in BEG files, there are none.
And,
I would say one of the main reasons is because service interactions are transient. So, you know, topics, public subscribers are typically something that is semi-permanent, while service invocations are basically ad hoc and transient. So it's very difficult to show them in this diagram because they could not exist at that point in time. Doesn't mean they're not important, obviously.
exactly. So I understand the point why they are not in that diagram, but I see a big problem in that there is no documentation of one of the two communication mechanisms in the framework that also.
That's just basic.
Yeah. But
That architect graph doesn't show, there's no excuse for not.
exactly. But I'm also I'm worried because the people that are learning ROS, then they have these tools, and then they forget that they have services to do some stuff that needs to be done via services rather than, I'm speaking from my student's perspective, right? So
The default is,
Yeah.
let's have a topic and you publish.
So it's kind of a reinforcement mechanism. So because we cannot represent services, we end up forgetting that we have services, and then all of a sudden everyone is trying to do control using publish subscribe, and in some cases it's just nuts, basically.
You mean coordination?
Coordination, yeah, sorry. Yeah. Coordinated control.
Just recently I saw this feature being introspection for services being added in ROS 2. I don't know if it was already merged, but there was still some discussion going on.
I saw that, yeah. There was a long time pull request waiting.
I just want to react to the smallest word you said as a person who doesn't have any robots in the lab. We said you can just run the RQT graph. I think that's very misleading. It's very easy to say for someone who is actually working on this project and has an infrastructure, but a ROS project cannot just be run in most of the cases. You miss the hardware and setup to just run it and inspect it. It's pretty annoying that you actually have to run it to understand the structure. I think that shouldn't be necessary.
Yeah. Okay, this is exactly what I wanted from to start talking also about how we can improve the ecosystem in some way in order to, you know, do something useful also from the scientific perspective, but also to the actual open source community. Yes, talking about that, I'm desperately looking for some ROSBEG 2 files. So if you have some in your pocket, or if you are planning to collect or to record some BEG files from ROS 2, please send an email to me, and you know, consider it some kind of a donation to science. We are going to run our tools on them.
We have some in the REMARO organization.
Okay.
Yeah.
Okay.
We collect on Thursday too.
Oh, that could
So
be.
following up on that, maybe we can collect data out of this event. So on Thursday we are doing a hackathon on an underwater robot running ROS 2. So maybe we should set up the bug system.
Okay, even tiny ones.
Tiny one.
Give me anything.
And get
Okay.
a REMARO acknowledgement.
Okay,
sometime
I
in
leave in the
future.
slide for 10 seconds more. So that Can I? Okay. Nice. I already spammed the discourse, so that's covered. Okay, I have some recommendations based on the what we saw in the documentation of the architecture. Visual is always keep it with you know, a grain of salt, but there is evidence that when there is a visual representation of the architecture, the decision process that you take on the architectural level, it's really improved. It leads to better decisions. So you can easily pinpoint you know, the pain points of your system. You can see easier in an easier way where is the bottleneck, and you know, in general it helps the reasoning on your system. Of course, when it's visual, try to use legends. We saw in the repositories many Frankenstein models without any legend or without anything. That was probably, less. It was more making damage than helping. So when you cannot trust an architecture documentation, then you have a big problem, because then your decisions are multiplied, but probably on the wrong side. So you need to be careful. To limit views to one aspect of the system. This is also something that is coming from the let's say the community, the software architecture community, where it has been proved that when you have Frankenstein models with different perspectives overlapping, like a computation graph organized in layers, or where you have also the hardware components, drivers, the communication with external systems that are not based on ROS, or if you put everything together, you might think you have a richer model, but this is hindering the understandability of the model. So if you notice that you are taking different perspectives when you are reasoning on the architecture, try to split this into two different models. So that is perfectly allowed. So we can have an architecture documentation focusing on the computation graph, and another one, for example, focusing on the relationship to the context, to the environment of the system.
Yeah, yes, a small comment on this. So this morning we talked about model-based, meaning that everything is in a centralized model that is very rich, but that was exactly the point of views. You don't want to show everything at a time, because that can be even more confusing for the purpose of communication. So that's why it's very important to limit the views to one aspect and use just different views, different diagrams to convey the different views of that single model.
Indeed, the last point is to have some kind of traceability between the views. So if you know that you have a part of the computation graph that is represented as a box in another view, try to have at least some kind of naming convention or something that helps you in easily mapping one element that you have in the model to the other elements that you have in other models. Okay, so these models are not islands completely detached. It's always it should be always obvious that they represent the same system. Okay, so navigating across models should be easy, and here you can do it in ranging from plain naming conventions to having some files only containing the mappings between the elements, or other ways that you might even invent them, but please do it. Okay.
Sorry, I was just going to say, or eventually use a modeling language.
Eventually. Okay. How much time do I have left?
Officially 3 minutes. We have 15 minutes break, so you can take 5 extra if needed.
I have a modular presentation. I can skip parts.
So done with 8 minutes.
Okay. Let's go to the guidelines. So what we did, as you saw before, we looked at all these repositories where there was some kind of architecture documentation. So 115. We sit for actually several days looking at these repositories, and we extracted a set of 47 guidelines for architecting ROS-based systems, and we organized them into 7 families. The one is about communication, how nodes should communicate, so what is the best way according to some non-functional requirements in how to plumb your system, how to split the responsibilities, how to reason about the internal behavior, and so on. This is one example of family. This is the one related to communication and networking. I'm putting the QR code here and actually a direct link to, let's say, a schematic version of the guidelines. So you will see only the tables as they are right now here. You will see basically the seven tables like this. And my dream, let's say scientifically speaking, is that when someone is working on a ROS-based system, this guy has, close to on his desk these tables, and once in a while coming back to the table and say, okay, this is what the best way to do something according to my specific situation. And in order for specific situation, here I'm also referring to the quality requirements. So for example, here we see that C4 is related to reliability, C2 is related to maintainability and portability, C1 is related to maintainability, portability, and compatibility. So this is the way I'm picturing the use of these guidelines, because we didn't do it just for the sake of spending time fiddling through several systems. We want these things to be read by people like you. I have some examples of guidelines. The first one of the communication family is suggesting to use standardized ROS message formats as much as possible, possibly supporting also their legacy versions. So we know that the standard message formats can evolve themselves, and then this is using standard message formats helps you in being a bit future-proof. But if you are already thinking to support the legacy versions, you are more future-proof. You know probably more than me that there are packages containing these standard message formats. And the idea to use them is because it increases the opportunities for reuse. So if I'm publishing point clouds according to the standard message format, because I don't think there is people doing it differently, but this is a very trivial example. So don't reinvent your message for point clouds, because then you lose all the opportunities for having, for reusing other components that are taking them as input. Or you cannot use already developed tools, for example, visualizers for the point clouds. It helps in testability, because if there are standard benchmarks already assuming a standard message format, you can simply use them with your node. And in general, it eases the integration of new sensors and hardware, because it's more probable that the people working on this are using standard message formats. So if in your nodes you are already using them, then the plumbing is already done. It's for free. You don't need to adapt the messages in order to use a new sensor, for example. So some of them might look very obvious to you. Some others might not. And this is exactly the point. So if tomorrow there is a new person working in robotics, you give this person the guidelines, is already, let's say, up to speed in a certain sense. It doesn't make the same mistakes that we did when we were working on ROS some years ago. Another example is about the family of nodes responsibilities. So the idea here is to group nodes and interfaces into cohesive sets, meaning that if nodes, there are subsets of nodes that are more or less related to the same functionality, try to keep them as close as possible without having strange dependencies to other nodes that don't have anything to do with them. Okay? Because in this way, basically, you can isolate the system into blocks, and you can, you have a better, let's say, mental model of the system, because you can really picture, okay, this is for vision, this is for navigation, this is for whatever. Okay? And it allows you to avoid reinventing the wheel. If tomorrow you are going to switch the package for navigation or whatever, if the rest of the system is already blocks of nodes that are well isolated, then it will be probable that you don't need to revamp the whole system if you are switching a package. Yes, this is an example from one of the systems that we analyzed, in which they divided their components into different layers. So this is one way in which you can start reasoning about how your system might be subdivided into these hypothetical blocks. Okay? Third example, internal behavior of nodes. So this is the name of the family. And this is the first rule. The behavior of each node should follow a well-defined life cycle when the node is stateful, of course. If it's stateless, the life cycle is just one state with a self-transition. which should be queryable and updatable at runtime. This is some kind of a bridge towards Ilias' presentation, which will be about self-adaptation. I'm spoiling it already. Because if you can query the status of a node at runtime, then you open the possibility to do reflection. So you can, as a system, you can look at yourself internally and you can say, okay, my state is, my internal state is this, then I can do something differently. Okay, I'm explaining very badly, but this is the job of Ilias on self-adaptation. Yes.
Okay. Commenting on the life cycle, so that's something that is not in the in ROS 1 in the core, but there are some libraries to implement the life cycle in ROS 1. Actually, one by Rosen, Jeremy, maybe you know about it, but they have one. But in ROS 2, this is in the
manage the nodes.
In every node you implement a life cycle.
This is a good point. Are you referring to managed nodes?
Yeah, managed nodes.
Okay.
Nodes have a life cycle.
If I remember well, in managed nodes, you can have 4 fixed states. That is already one step, which is good. I think it's active, inactive. I forgot the other 2.
Yeah, configuring, right? To configure.
Yeah.
But
okay.
there is an extension by BOS called system modes that extend the active state to support different modes of being active.
Okay.
Different states. And we use that in our
that is good.
meta control for self-adaptation. Ilias.
That can be seen as a way in which you can, implement a guideline. So, and that's the best case, because then you have a library that you can reuse across different systems. So this is really the best case. Okay. I think I'm gonna stop in here and leave the rest to as homework. Because if I start this topic about architectural tactics, I think I'm gonna still 1 hour.
Do you have a one-liner or one summary slide?
Yes. What is an architectural tactic for us is, imagine you have this system. It's very trivial, but you have the drivers, the slum, and some areas in the architecture. An architectural tactic is a specific design decision that is targeting a non-functional requirement. For example, we might have a tactic where we say, okay, all the business logic for the obstacle detection will be always moved to the cloud, and the type of non-functional requirement that I'm improving is energy, according to the first experiment that we saw in the talk. Okay, so based on that knowledge that we accumulated, we say, okay, we apply the tactic that if in version 1 I was having obstacle detection locally, after the application of the tactic, I moved it all to the cloud. Or another one is about availability. The tactic is called heartbeats, and this comes really by the book. And the idea is that if you want to know that all the robots are always up and running, one way in which you can implement the tactic is in which you can have this kind of achievement in terms of availability, is to have to promote a node as a diagnostic, a robot as a diagnostic robot, and then to have the other robots sending once every 10 seconds or whatever a message, even an empty one, an empty message telling I'm alive. That is it. That's a very basic implementation of an architectural tactic for availability. Because then if after a certain delay you don't receive any message, any heartbeat from robot B, then you know that robot B probably is dead, is offline, he crashed or whatever. And then as a diagnostic node, you can take some measures to solve it. Okay? But the tactic is a very tiny design decision. So here is every robot sends an heartbeat message to one other robot. That is it. And just a trailer, a teaser for the experiment. What we did is this. We identified 4 tactics for green robotic software for saving energy. You can read the paper if you want to see the details. And after that, we implemented the tactics, and we did an experiment to check if the tactic actually works in practice. This is the difference between a guideline and a tactic. A guideline is very abstract. You should do this, you should do that. And it's based on qualitative information. With the tactic, it's something that you can put in action in a system. And after you implement it, you can measure and you can see if it works. Okay, so that's really the difference between a guideline, which is a rule, and a tactic, which is something that you can really embody in the system and measure. And we discovered that the combination of the tactics, no big surprise, leads to the most energy efficient robots according to our experiment. So tactics can be also combined. So you cannot just say, I apply tactic 1 and the rest are turned off. You can apply multiple tactics in your system, and this is exactly the process of architecting a complex system. You always apply tactics based, hopefully, on some knowledge that is coming from science. I think I'm done.